The Quantum Leap, Schrödinger's Cat and the Future of Computing. Welcome, everyone, to Quantum Quest, your journey into the fascinating world of quantum mechanics. I'm your host, Alex, and today we're diving into a groundbreaking discovery that...
So, this is it.
This is a quantum computer.
This is a quantum computer. Here I am seeing a real-life quantum computer for the very first time with my friend.
Thought experiment to illustrate the strange nature of quantum mechanics. Imagine a cat in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers, releasing the poison and killing the cat.
Finally understanding why quantum computers are such a big deal.
Quantum computers.
Quantum technology.
What on earth is a quantum computer?
Bits, qubit. Try all the codes at once.
Whichever nation first develops a practical quantum computer.
Why governments around the world are battling it out to build them the fastest. Quantum computers are wild. They're on track to change what we can build and how we understand the world. They're kept at temperatures colder than space. But if you think you...
According to quantum mechanics, until we open the box and observe the cat, it exists in a superposition of being both alive and dead. Cat meowing now, fast forward to the present day. A team of researchers led by Professor Andrea Morello from the University of New South Wales has taken this thought experiment out of the theoretical realm and into the lab. Laboratory ambience. Professor Morello, welcome to Quantum Quest.
To my knowledge, the largest quantum computer that exists, which I say with confidence, like I know what that means.
I was gonna say, what is biggest? Because like I heard, like supercomputers, they're massive rooms full of computers, and when someone says we have the biggest supercomputer, I'm like, oh, I can picture that. The largest quantum computer, I'm not even sure what to picture.
Understand what quantum computers are good for. Imagine that you're on a video game map, and how you get around depends on how good you are at doing math. You may not want to play this video game. Bear with me. So first, there were no computers. Things like geometry and astronomy took forever. So you have your little pencil and paper and you're traveling across the mathematical map by walking. So it was slow. And there were lots of areas that we just couldn't explore because it was beyond our computational ability. But then we developed early computers, and that allowed us to input larger data sets and answer problems that had previously been out of reach. These new computers unlocked new areas on our mathematical map. Instead of walking everywhere, we can now ride horses. We can get farther faster, and we can access areas that were previously inaccessible. But there were still parts of the map that our computers couldn't access. Luckily, computers just kept getting better, and they allowed us to solve more and more complex math problems. As a result, our virtual map has transformed. We have roads and cars, and we're just reaching areas that were previously unreachable. Better computers mean traveling across this map faster and more easily than ever.
The thing that he said was really important to understand is that quantum computers are not faster cars, they're boats.
A boat is not necessarily better than a car. They're just built for totally different terrain. So with our new quantum computers, we're beginning to navigate these new mathematical waters, solving problems and discovering areas that traditional computers just can't.
My question for IBM is, what's in the water?
Oh, wow.
What are the oceans that we're all of a sudden able to explore with our quantum computer boats?
I love this. I'm an analogy person, so I'm like fully absorbed in this now.
Can you tell us about your recent breakthrough? Professor Morello, our team has been working on a way to use an antimony atom as a qubit in a quantum computer. Antimony is a heavy atom with a large nuclear spin, which means it can take 8 different spin directions instead of just 2 like a regular qubit. This opens up new possibilities for quantum computing. But how does this relate to Schrödinger's cat? In our experiment, the antimony atom's multiple spin directions act like the cat in the box. Instead of being in a simple superposition of 2 states, it can exist in a superposition of 8 states.
So this is the lab.
That's a quantum computer?
Yeah, but actually this is a dilution refrigerator. This whole thing is basically constructed to keep the quantum computer very, very cold. 15 millikelvin. It's the coldest thing basically in the universe. It's colder than outer space.
So inside that is 15 millikelvin?
Yep. So here, let me show you the one that we can like play with.
This is it.
This is a quantum computer.
This is a quantum computer. The quantum computer is a chip in this one here, but this whole thing keeps the quantum computer working at insanely cold temperatures like we talked about.
So this is all refrigerator technology.
So all of these cables that you see here on the side carry signals down through the fridge into the processor, and then they do their quantum stuff, and it comes up. And it goes to these room temperature control electronics, and they turn it into things that humans can understand.
That is a quantum computer. We were allowed to touch it, which was cool.
Oh my God.
So I think it's really funny that when people generally talk about like the difference between classical and quantum computers, people are like, okay, well, you know how a classical computer works, right? But like the truth is that like nobody knows that. A simplification of it is it comes down to bits. And bits are made out of pieces of silicon, and you have, you know, tens of thousands to millions of them in your computer. And they can either be in the state 0 or 1. We call it the ground state or the excited state. And everything that you type into your computer, like all words, all numbers, all colors, get translated into computer speech. But it's very binary, right? A quantum computer is run on qubits.
Qubits aren't like bits. They aren't a 1 or a 0. They're more complex. Think of this like a wave. A qubit could be really likely to be 0, which means a lower energy wave. Or it could be really likely to be 1, which means a higher energy wave. And each qubit has a probability of being each. When a quantum computer is working, the probabilities of multiple qubits interact.
And they add constructively or destructively, just like waves would. If you were to like tap like 2 places in a pond.
You know how when you like explain something to a 2-year-old and they just keep going, why? And they have to explain it again and you go, why? Yeah. My question is, as the controller of the computer, you decide what about those probabilities?
Basically, you are altering the probabilities while you're running an algorithm.
It's a common misconception that quantum computers try all the options. That's not right. This is simplified, but it's more like a quantum computer kind of watches the pond. It watches how all of those waves interact and then finds the most likely answer. If this is all confusing, don't worry. All you really need to know is that quantum computers calculate things very differently than classical computers do, and that makes them good at different things.
Quantum computers are not going to be faster at everything than a classical computer. Like, it's not good for addition, right? Because your calculator and your phone is perfectly good at that. But the things that quantum computers are good at is finding structure in tons of data. And if you're interested, we can close it back up.
Absolutely. Put us to work.
Let's go back to our virtual map.
Traditional 2-state qubit system, a single error can cause a catastrophic flip in state. But with our antimony atom, it would take up to 7 consecutive errors to misinterpret the state. This provides a buffer that can absorb minor errors without causing the system to fail. That's incredible. And what about scalability? How does this fit into the bigger picture of building large-scale quantum computers? Professor Morello, we've embedded the antimony atom inside a silicon quantum chip, similar to those used in conventional computer processors. This means we can leverage existing semiconductor technology to build and control these quantum systems. It's a significant step towards scalable quantum computing. This sounds like a game changer. What's next for your research? Professor Morello, our next goal is to demonstrate a method for detecting and correcting errors in our chip. This is considered the holy grail in quantum computing. If we can achieve this, we'll be one step.
So we have our boats, and we're floating around discovering new parts of this map. One of the first new areas of interest is simulating nature.
Simulation of nature seems really interesting. Why is nature one of the things?
So nature fundamentally is quantum, and it obeys quantum physics. We just don't normally see it. But if you look at like a molecular level and like the atomic structure of molecules, everything has to follow the laws of quantum physics. It's really hard to calculate what a material or what an atom is going to do past a certain size. So at a certain point, it just can't do it. But if you're interested in like developing battery technology or creating new materials that have, long chains of molecules, you're going to need a quantum computer.
This is why people are so excited. Think of the new materials or medicines or molecules that we could make if we could better predict the way that nature behaves at a molecular scale.
Oh, yeah.
Yeah.
There you go. Boom.
Okay, so simulating nature is something that quantum computers could be amazing at. But we're also getting closer to another use for quantum computing, one that people and governments are more concerned about.
Completely new encryption algorithms.
Break encryption.
Quantum-resistant encryption.
A fully functional quantum computer could be built with code-breaking capabilities that could render all forms of online encryption unreliable.
Okay, now this is the one that I've been waiting to ask about. Okay. Why is everybody so obsessed with talking about quantum computers and encryption?
So the first major algorithm that was developed for quantum computers is Shor's algorithm, named after Peter Shor. Super nice guy. He invented an algorithm which basically can find factors, prime factors, for really large numbers. Why does anyone care about this? Because that's the basis for RSA encryption, which is basically how all transactions on the internet are conducted. And the entire reason that all of our encryption schemes today work that way is because it's basically impossible to crack that with a brute force classical algorithm. It would take, I think it's like billions of years. But a quantum computer could do that way more efficiently. We're talking hours to days.
So this global race now makes a ton of sense. Whoever gets a quantum computer to actually do this has a big, obvious advantage.
But we haven't done that yet. That's one of the ones that requires probably like 1 million qubits or more to do, but we're working up to it.
So we're not going to be using quantum computers to break all internet security right now. Today, we're at 433 qubits, the record set by IBM. 400 to 1 million qubits is a big difference, but Olivia is confident that we'll get there sooner than you think.
In the next 5 or even less years, we're going to see people switching over to quantum safe algorithms because of this reason.
So RSA goes away and we have quantum safe encryption instead?
Probably. Not all at once.
Yeah.
But gradually, you're going to see people do it. We're progressing at an incredibly fast rate. We're solving problems that people didn't even begin to know how to crack 2 years ago. But we've done it. Like every single year, everything that we say we do, we do. Nothing mathematically or physically prevents it. And so if the physics says it's allowed, the engineers will find a way.
That's sick. I'm adjusting the analogy slightly, that it's submarine because there are sort of different levels of quantum computing.
Yeah, we are just skimming the surface. We're going to keep iterating and improving upon this technology every single year. And we're probably going to discover like new applications that we haven't even considered yet.
It's a bottomless ocean.
It's a bottomless ocean.
Complexity allows us to build more robust quantum systems that are less prone to errors. So, this could solve one of the biggest challenges in quantum computing, error correction. Exactly? In a traditional two-state qubit system, a single error can cause a catastrophic flip in state. But with our antimony atom, it would take up to 7 consecutive errors to misinterpret the state. This provides a buffer that can absorb minor errors without causing the system to fail. That's incredible. And what about scalability? How does this fit into the bigger picture of building large-scale quantum computers? Professor Morello, we've embedded the antimony atom inside a silicon quantum chip, similar to those used in conventional computer processors. This means we can leverage existing semiconductor technology to build and control these quantum systems. It's a significant step towards scalable quantum computing. This sounds like a game changer. What's next for your research? Professor Morello, our next goal is to demonstrate a method for detecting and correcting errors in our chip. This is considered the holy grail.
Mathematics and physics and science was equivalent to other steadily advancing forms of transportation around our imaginary video game island, but I liked adjusting to submarine because there are levels to it. It's more of a bottomless ocean in that we're just gonna keep going. The tech gets better, there's no physical limit, it just continues to improve.
Here's how Olivia put the dream of how we'd actually use quantum computers.
It's beautiful because, like, of course, we all want to make the world a better place. We want to develop technology that's gonna enable us to do fundamentally different and better things. But it's also beautiful because, like, part of the human experience is you just want to, like, learn what we are and, like, learn more about the world we live in. And the fact is, the world is quantum mechanics.